So in case you didn't know me, my name is Alex Ward. I'm going to give you a review of catalytic reduction of carbon dioxide using organoaluminum and gallium compounds. But I'm going to try to focus a little more on the aluminum because the gallium, they didn't really talk as much about that one. So kind of the general idea behind the reaction is carbon dioxide, as you know, is a greenhouse gas. Well, so let's try to find a use for that kind of idea. So previous studies have been done on it, catalyzing with dihydrogen or hydrogen silanes, but the new idea of using main group metals or some metal-free catalysts is kind of new. So as you can see, this catalyst over here is using the gallium metal, but it's kind of a larger complex, mostly for some kind of protecting of the metal complex. So that way you only have to worry about one side and it can do its thing. So as you can see, there's the carbon dioxide kind of reacting with the triethylsilane there under those conditions with the catalyst to give some products. Now they did end up giving a couple different products, but the goal was to get methane out. So some of the kind of requirements for it, so for it to be an effective catalyst, they decided that the coordinate, it had to be pretty much unsaturated, at least in one spot. So, you have to have a space for something to come in and bind and then, do the reaction, and then it has to separate again. So that's kind of one of the reasons they mentioned here that for the catalytic activity to really occur, it had to be more of like a Lewis acid. It had to be able to donate that lone pair electrons, which is why I said that the gallium wasn't as efficient because it's less acidic in that sense, whereas it has a d orbital and aluminum does not. So that's kind of the reason I decided to focus on the aluminum. So by separating the cation and anion, you kind of like decrease the stabilization of the metal heme, so allowing it to undergo that catalytic reaction. So if you're going to do that, you want something that's weakly anionic, so that way it can separate easily. So they use a whole bunch of these huge compounds here, and so fluorinated tetraphenyl borates. Problem with these was they would decompose a lot of the time, and some of the carbon anions with chlorine and bromide, which is one of the ones we'll end up looking at in this paper. So kind of the formation of the metal complex, there's the general kind of reaction laid out there. It's basically the same process for both. So I don't know if you can see it over here, but you're just going to react this aromatic group over here that has a lithium attached to it, basically with a chlorinated metal compound with two ethyl groups off of it, and that's just going to give you your kind of starting material, I guess, for this, and then lithium chloride. I forgot that. So, and then it's the same idea for the gallium compound, only they use the dip group, which is that huge thing. So kind of what this was saying then is, in order to form the actual catalyst, then you take this aluminum complex we just formed, and then it has to undergo an ethide abstraction, so that way you open up a site for the reactant to come in and bind or coordinate and then fall back off. So they used a couple different R groups here to make this happen. This is one of the ones I focused on, this huge aromatic group here with the aluminum center, and like I said, because the gallium does not it's less acidic, so it doesn't react as quickly. And they also kind of determined from this that these larger groups, they slow down the reaction because they're sterically hindering. And yeah, that's kind of the basis behind that. So the ethide abstractions, basically, you're going to have this, you're going to have your starting material, you're going to have your huge anion here, pick up a hydrogen, from the triethylsilane, and then it's going to kind of separate, and this is going to come over here, your silane group, and pick up this ethyl off the aluminum, and then give you your catalyst, which is weakly associated to your anion here, and then spit out this tetraethylsilane. So these were just a couple different structures they ended up getting when they tried to do this with some other compounds, and this was just kind of showing the stabilization of the aluminum. So they didn't want it to be too stable that you couldn't dissociate from your anion, and it wouldn't be as effective of a catalyst. And I kind of just picked this because this was one of the closest to the ones in the paper, where they had this aluminum here forming, what do they call these again? They call these, one second, some type of bridging. It had a specific name to it. I'm sorry, it's escaping me right now. But basically all that does is it stabilizes that state, which, if you have an anion, you don't want negative things over there. So it's a little less effective. So the bulky groups here, as you can see, they did something similar in another paper where, that's what it was called, the adduct here, these bonds to the aluminum, just kind of helped stabilize that so it can undergo the reaction, and then it would just undergo the ethide abstraction. And this is kind of like the overall arching idea I was trying to show over here, but I was not going to draw that thing. It's just not going to be. So it just kind of weakly coordinates there to that aluminum center and stabilizes that state until you have your triethylsilane come in, and then it can start that catalytic process with. So, of course, like I said, the gallium kind of feels left out because most of the time they just use it as to get structures from, because it's not as effective of a catalyst. They said as you increase, as the complex activity increases, the coordination number tends to decrease. So they were attempting to make a 2-coordinate organoaluminum complex with some of these bulky substituents by trying to kind of like go or wrap around it. So they made the prototype using gallium because it's less effective. And why not? So, let's see. I called this the vicious cycle because it's very repetitive and kind of was like, what the heck was going on for the longest time? So, to get a better idea of that, I'm going to try to explain that via this chart. So, basically you're going to end up reducing carbon dioxide a lot. So you're going to have carbon dioxide come in here, and it's going to kind of cause the separation between the cation and anion, and it's going to basically stick itself on the aluminum. And then because aluminum is electron efficient right here, it's going to kind of pull the triethylsilanes, kind of close it. And that's going to allow the hydrogen from this triethylsilanes to come over and attack the carbon. And then from there you can get some rearrangement, and then this carbon dioxide can pop off, you can reform your catalyst, and then this silane's like, hey, I need some electrons. The oxygen's like, I got you, bro. We're gonna make this work. Your catalyst is reformed, and you have reduced your carbon dioxide to form this, basically adding on the triethylsilane group to it. And so that's kind of what you see popping out here. And then they're like, well, let's do that again, and again, and again. All the way till you effectively pull off all of those oxygens, and you're just left with your methane group there. So they did a couple side reactions using some deuterated benzenes, and just formed some other odds and ends here. But for the most part, it's just a continuous reduction of that carbon dioxide. So the ethyl group that said on the triethylsilanes was going to kind of fill a vacant site. Pretty much went over that. It's just slowly progressing there towards that methane. So yeah, and basically it wasn't the most effective, so that's why I believe they said here that these were the other products they kind of went for, because they only ended up getting this methane here in a 20 to 30% yield. So that was kind of based off of this previous work here where they called this the frustrated Lewis pair system. I wonder why. So this was one of the earlier attempts to transform the CO2 using the hydrosilane as the reducing agent. So they would sometimes end up deactivating the systems with water because they had alcohol groups and some other things. So like I said, just very similar process, just different anion. So kind of after testing the reactivity and stuff, they found that the activity of this aluminum complex was at least one order higher than some previous compounds they had used. So the X is, the chlorine or iodine, and because it had to do with the basicity of the this huge thing over here, the dechlorinated anion. So and then the catalytic activity of the complex is basically determined by its ability to accept the lone pair electrons as well as separate from its counteranion. So kind of just that right balance between attraction between the ions and then its ability to accept or donate a lone pair is what's really going to make this process work. That's all I got.
So, what their whole goal is to take CO2, but like out of this like atmosphere or something like that. Why do they want to react with CO2?
Well, because for one reason, I had seen some mentions of it in some other papers where they're like, hey, this is a greenhouse gas, so can we do anything to use this? So they're like
methane, then, which is another greenhouse gas, is their end product.
Because I guess because they can use it for some others, from other reactions, other organic chemistry reactions. I guess you can build off it as well. So,
Fair enough.
Can you go back to your last, the borate?
Last slide.
Yeah,
This.
yeah, that one.
Okay. This is basically a carbon copy of the slide I had before. They just used a different. I know, organic kids. But
So what was the issue between the direct issue between their borate mechanism and their aluminum?
So here they weren't using it. I followed this because they kind of followed the same process going on here, where they were just showing the reduction of the carbon dioxide using these different anions. And I was looking at some of these papers and I was like, how? This is oddly similar to this. So
Okay, so they didn't reference the
yeah, they just
borate.
kind of referenced it and did this a similar process. The only difference here is that they were reforming a non-metal catalyst. So that's all that's happening right here, and then they can get back to what they started with. But after they get out of this cycle here, they just are essentially doing the same exact thing. It's just a different method to get there. And as I said, I think at the beginning of the paper here, so they have used basically main group metals, and the idea of using metal-free catalysts is kind of a new idea as well. And I think that is what they were going for there, is using the non-metal route. But the process was pretty much the same.
Is there a reason they started with the triethylsilane, or is that just what
yeah.
they?
So I think they had used methanol before in some of the papers. They were talking about that, and I think I said it in the last slide. That you ended up, where did I put that? I think right there. You ended up getting some byproducts from like alcohol systems that would end up deactivating the catalytic cycle, and then you weren't able to continue the process would stop.
Can you go to the slide that had all the R groups?
Yeah. It's down here somewhere. No. We'll find it.
Where are they?
I don't know, they just disappeared. They said, we're out, peace.
Yeah,
Come
where are
on. Start at the top.
Keep going up. Next one.
That is-
There you go. So, did the larger R groups, because they seem to be using large R groups, like, why did, like you said, it slowed it down?
Well, they tended to end up slowing down the reaction slightly, but they protected the metal so you didn't get some other odd products.
Okay, so it's to more reproduce the catalyst?
Yeah, it's more selectivity issue than it is catalytic reactions.
Okay, and then, I don't know what I was writing there. Where does the oxygen, can you go to the mechanism again?
Over here.
Or-
Because, yeah, I didn't draw on like everything I wrote down
Yeah.
because it's just,
I think it was
really
on the other
repetitive.
side, I just didn't see it.
Yeah, so you have your carbon dioxide.
Mhm.
The owner was like, hey, you take this, I'm electron deficient.
But I mean, where does the oxygen, because you said it keeps going through until the oxygens are all gone. Where
Yeah,
does the
so
oxygen-
you're just gonna keep throwing this on here, so see how like he lost the bond of the oxygen here?
Mhm.
So now if you go through a third step, wow, that
I think if you put up your cycle slide,
Yeah, I think
you'll be
it's on
able
there, I
to
just-
better show where the oxygens go since they're highlighted in red.
yeah,
Or
so
blue, rather.
right here after the third step,
Mhm.
you're gonna see this pop off. You're just gonna,
Okay, so you just lose that extra bond, okay,
and then you put a hydrogen there.
gotcha,
And then the fourth, you completely get rid of that, and that's where your methane comes from.
okay.
So they're continually going to the silane?
Yeah, they're just continuously, using that to reduce the carbon dioxide at each step there, and they're just using this metal complex to catalyze that reaction.
So can you go back to the one with the chlorines bound, like the addict or whatever you call it?
Oh, yeah. So here's a couple different addicts. I mean, it doesn't have to be in between that. It's just the kind of like ion coordination.
So you said C is the most stable? Or,
C was the most similar to the compound that we were.
okay, so
The ice
they didn't like choose between these things?
Okay,
These were
yeah,
just-
that's what I-
okay.
Yeah. No, they didn't choose between these three. It's just they referenced this paper, and I saw that. I'm like, well, that's eerily similar. So, and they mentioned in the paper they used the unchlorinated form.
So go to your next slide.
Like I said, it's just, this is what they did, they formed it, they really didn't go into detail about how this happened, so that was a struggle to try to figure out. So I had to actually go talk to KMAC about that one.
So, my, like, I don't know if you can answer this, but like, where the chlorines are now, if you could make those groups more electrophilic and pull even more from the like the ring, could you make the aluminum even more positively charged? You know
Well,
what I'm saying? Like, could you, like, make it almost like a
aluminum really
dipole?
only likes to be +3, so you might have a struggle doing that. But, I mean,
I mean, if you have like,
the issue with that is, like I said, stability, like, they're just kind of stabilizing
Yeah.
this state. So, I mean, if you make it too stable, your anion is not gonna wanna come in, and then you're not gonna wanna bind to anything, so it's useless as a catalyst.
Yeah.
So, I think that's kind of why they went with the unchlorinated form, because while this probably would undergo the same process, you're not going to be as effective at doing it.
Go forward a couple. Go back one, I guess. So the major product for all of the catalysts that they used was that silyl ether there at the bottom with methyl on one hand and
Yeah.
then your triethylsilyl group on the other.
Because I'm assuming they just were like, hey, let's go through here. Well, we weren't getting so much of this over here, but if we just continue this process, hey, we got a lot of this, we can do something with that, but no, we're good. Because you can pretty much stop at any point and just have that as a product. And they just mentioned they got a lot of that. They didn't say why, they just, hey, this is one of our major products.
What were the reaction conditions that they were using for the, I know you mentioned them toward the beginning, I'm not sure if that
I
was
wouldn't
the case
say
for all of them.
I didn't look super in depth into that, but it was relatively mild conditions. It was just the catalyst at, 80 degrees.
And this is run under some kind of CO2 pressure?
Yeah, I think they said it was 1 atmosphere, so it's relatively mild conditions that this occurs under.
Okay. So in the paper, their catalysts don't give methane as the major product. Do any of the prior catalysts that were studied give methane as the major product?
No, I think that's one of the reasons they were trying all these different methods, is that they were getting it in pretty low yields. So, like here, it was only 20 to 30%. I think some of the other ones were like in the 10s. So I guess they're trying to figure out the most effective method to do this. And they're like, hey, well, we didn't quite get what we wanted, but we got a lot of this.
So as far as major product goes, I guess the terminology is almost, it's the major product just because its percentage is the highest, but what is our product distribution between those, let's say, 4 or 5 different materials that you're kicking out from this cycle?
So I want to say that, so that's like 20 to 30. I want to say this is, the major product's close to 50 and the other one's like 40 to 30. So the minor product's like 40 to 30.
I think it's even lower than that. I want to say the major product for most of them ends up being around 40% max. Your minor one over there is normally around 20, and then you have some residuals. It's actually funny if you look at the table and add up all the percentages, they don't add up to 100, so there's actually other products that are being formed that they don't even care about, and they're low enough concentration. How do they follow this?
How do they follow it? I haven't hard enough time following it, so I don't really know.
No, but how do they determine all these?
What do they
As
determine
far
all these?
as
They used
what's
they used X-ray diffraction. They were checking like crystal structures for some of these.
But
so they
specifically for the catalytic reactions?
Oh, NMR.
What is it? Okay, yeah, they use NMR.
So
So they're
most of these
just,
were they mentioned were done in like NMR tubes.
yeah, and they're actually really special NMR tubes because they have to be under that 1 atmosphere pressure that you were saying. And then it's actually temperature controlled since they ran them at higher temperature, so it's kind of an interesting experimental setup.
They said it was like 2/3 of the tube was kept at that temperature,
Mhm.
and then like the rest, I don't know.
That
They
was
just-
expensive.
So the interesting thing about these guys is the fact that, I'm not sure if you guys kind of caught this, is that it's a cationic, well, it's an ionic system, but the solvent that's being used is extraordinarily nonpolar benzene.
Oh, yeah.
It's a benzene.
Mhm.
Oh.
So do we expect benzene to be able to solubilize ionic salts generally? No. So what they state this means is that if you go back to your pretty picture of the cation anion pair, what this means is that when it dissolves into the benzene, that the cation and the anion are staying relatively close together. Insofar that plus and the minus are together, it's kind of neutral if they're right next to each other, and therefore can be dissolved by a relatively nonpolar solvent like benzene. On the other hand, they do make the assertion that they want the cation and anion to better dissociate from one another because that leads to an increased reactivity as far as the catalyst goes. If they're too tightly bound, it makes it difficult for the substrate to get in there and interact with either the gallium or the aluminum.
Why are they using benzene?
Because it kind of like you were saying, it protects. and
They
that's
want to
why-
use benzene, they can't use many other solvents because those other solvents will react with the Lewis acid as well, which is why water was such a problem, or methanol, or anything that really has an electron pair that's good at donating. And even benzene is problematic if you go back to your cycle, Alex. All those off reactions from the products that they wanted are dealing with benzene being a non-innocent ligand. So you see C6D5 being incorporated into a few of the side products there.
So they kind of just deuterated it to see, hey, we have it in solution, we're trying to protect it using this solution, but it's still reacting, and
Yep.
they're using the deuterium to kind of see what it's doing.
Yep.
Is DCM then a reactant?
I don't know. Yeah, I would assume you would get, some chloride abstraction in that case. Even in solution, DCM, carbon tet, all those will normally have a chloride radical, which I'm guessing would play havoc with this.
Well, you already had it in forming those adducts in the other ones, so you probably just,
Yeah. Yeah, and this guy is going to be fairly reactive. Last question I was going to ask, I know we're kind of eating into your time, Adolfo, here. They state that these processes can occur even with just tri-substituted boron or tri-substituted aluminum. What's the benefit of having this di-substituted cation versus the tri-substituted neutral compound acting as the Lewis acid?
Just for a second. Can you repeat that?
So your active catalyst, like, we don't really care about the anion,
Yeah.
but their active catalyst is this di-coordinated aluminum cationic substance. They state in the paper that they see the same type of reactivity can occur with Lewis acids that are the normal tri-substituted, like some kind of tri-substituted boron or aluminum. So why is it that we would want to go to, say, a di-substituted cationic versus the neutral? I guess,
it was. just
which one's the better Lewis acid, I guess is what I'm asking.
What would be the aluminum?
But the neutral one or our cationic one?
The cation one.
Right. So that's, I guess I wanted to know what the efficiency difference is maybe, but maybe they didn't report that.
I don't recall that, but I'm just.
Okay. But yeah, if you rip off an R group and make that metal positive, I mean, that's going to make it even more of a Lewis acid as far as it wanting electrons.
I just know that's like why I didn't focus on gallium as much, because you rip off some electrons of that, it's like, hey, I got a D10, I'm good.
Yeah, the gallium one is an interesting one. It seems to make a dimer, which I guess reduces its activity a little bit.
So if you took off that ethyl group, you would make it too strong of a cationic pair? Is that what?
From here?
Yeah. Like, would that make it too,
So if we made it a 2+,
yeah, would that make it too strong?
I'm not
Until it, like,
I'm not sure what we would do with that one. Yeah, that would probably want to react with
Well,
a bunch of other things at that point. But I don't know. I'm not sure if anybody's looked at just a single R 2+ one. That might be difficult to prep though, you're right. I'm not sure how
Well, I think
stable that
that's
would
what
be.
the one research paper was going